Welcome back to the Basic Electronics series. In today's session, we will learning about magnetic circuits and electromagnetic induction. So here is the agenda: magnetic circuits, comparison of magnetic and electric circuits, properties of magnetic circuit, electromagnetic induction, Faraday's law of electromagnetic induction, Lenz's law of electromagnetic induction and Lenz's law experiment, dot convention in coupled circuits. So this diagram represents the magnetic circuit. So magnetic circuit is a closed path through which magnetic flux flows. So here it consists of a magnetic material. So generally an iron core. So it is used for making solenoid part of the circuit. The solenoid with N turns creates magnetic flux, that is nothing but phi. It generates the current I in the solenoid. So this is the current I. So this is about the magnetic circuit. And next is the comparison of magnetic and electric circuit. Here you can see this is the electric circuit and this is the magnetic circuit. Here we having current I, but here we having magnetic flux phi. This is voltage and this is the induced voltage or EMF. And this is the resistance, and here we having reluctance. So in electric circuit the current is flowing, right? Electric current is flowing, but in the magnetic circuit the magnetic flux is flowing. So we have Ohm's law for electric circuit is V equals to IR, but in magnetic circuit we having F equals to phi into R. And in electric circuit we having force involved in maintaining circuit is electromotive force. But in magnetic circuits we having magnetomotive force. And see, here we having resistance. So it is used for the opposition of flow of current. But here we having reluctance. It is used for opposition of magnetic path to flux. It is opposed by the magnetic path to flux. In electric circuits, the flow of electrons decides the current in conductor. But in magnetic circuits, the magnetic lines of force decides the flux in the core. So next is the properties of magnetic circuit. So first is the magnetic flux. Formally, magnetic flux can be defined as quantitative measure of magnetic field lines passing through a given region. So it can be represented by a symbol phi, and it can be written as phi equals to B into A B dot A dot cos theta. So this picture shows how an induction cooktop heats a pan using electromagnetic induction. So here we having AC supply and this is coil. So the alternating current, so here we having, right? So this flows through the coil below the cooktop. Because current keeps changing the direction, the magnetic field also keeps changing. So this change in magnetic field is called changing magnetic flux. So this magnetic flux moves upward from the coil. So when an iron pan is placed above it, the flux passes through the metal pan. So the pan is inside the magnetic flux. So when magnetic flux changes through a conductor, it induces a current. So these current inside the pan are called eddy current. So this is electromagnetic induction. The metal pan has resistance and the eddy current produces heat due to this resistance. So pan becomes hot directly, not the stove surface. So we can say it as changing magnetic flux from the coil induces currents in the pan, and these currents produces heat due to resistance. So in simply we can tell like, so AC current in the coil produces change in magnetic flux. So this flux passes through the pan and induces eddy currents. Because of resistance in the pan, heat is generated and cooking happens. So this is about the magnetic flux real-time example. So next is the magnetomotive force, that is nothing but MMF. So it is the total magnetic potential difference in a magnetic circuit. So it is used to perform the task of maintaining magnetic flux in a magnetic circuit. So the formula for magnetomotive force is given by F equals to N dot I. So F is nothing but magnetomotive force. The unit of F is nothing but ampere turns, AT. And N is nothing but number of turns of the coil. And I is nothing but current flowing through the coil in amperes. And next is the reluctance. So it is also like resistance. So reluctance is opposition to flux. Resistance is nothing but it is the opposition of flow of electric current. So it depends on length, area and permeability. So the unit of reluctance is ampere turns per Weber. So it might be asked in interview, so remember the unit of reluctance. And next is the Ohm's law analogy. So phi equals to magnetomotive force by reluctance, that is nothing but phi. So next is the application. AC generators, electrical transformers, magnetic flow meter, these all are based on the principle of electromagnetic induction. And next is the electromagnetic induction. So what is electromagnetic induction? So it uses the relationship between electricity and magnetism. So the name is electromagnetic. So here electric current flowing through a single wire will produce a magnetic field around it. So that is nothing but electromagnetic induction. So the magnetic flux developed around the coil being proportional to the amount of current flowing in the coil's winding, that is shown in this figure. So in simply we can say that electromagnetic induction means producing electricity using changing magnetic field. So see here, the magnet creates magnetic lines of force. So these lines passes through the coil. So when the magnetic moves or coil moves, the magnetic flux through the coil changes. So this change is very important. So due to changing magnetic flux, electricity is produced in the coil. So This produced electricity is also called as induced current. So when magnetic flux changes in a conductor, electric current is produced. So this is called electromagnetic induction. So next is the Faraday's law of electromagnetic induction. There is two laws. First is Faraday's first law of electromagnetic induction, and next is the Faraday's second law of electromagnetic induction. So the first law states that whenever a conductor is placed in a varying magnetic field, an electromotive force is induced. So if the conductor circuit is closed, a current is induced. That is called induced current. Here you can see changing the magnetic field intensity in a closed coil. So this is the ammeter and this is the coil. So this is the magnet. The direction of motion for a magnetic or coil is represented here. And next is the Faraday's second law of electromagnetic induction. So the induced EMF in a coil is equals to the rate of change of flux linkage. So this is induced EMF, which is represented using the symbol epsilon. N means number of turns and delta phi by delta t represent rate of change of flux linkage. So flux is nothing but phi. So this minus sign shows the direction, not magnitude. It means induced voltage always opposes the change in magnetic flux. And next is the numericals. So this might be asked in interview. So the induced voltage across a coil with 250 turns that is located in a magnetic field that is changing at a rate of 8 Weber per second is. So we having number of turns, right? That is nothing but N, and rate of 8 Weber per second. Weber, it is nothing but the unit of flux, and this is unit of time. So rate of means it can be represented d phi by dt. So d phi by dt is equals to 8 Weber per second. Now from the Faraday's law we have a formula EMF epsilon equals to n delta phi by dt. Here no need to mention the sign minus because it represents the direction, not magnitude. So substitute the values. N means 250 and d phi by dt is equals to 8. So now induced voltage or EMF is equals to 2000 volt. We can also write it like that, 2 kilovolt. And next we having another numerical. So what is the flux density when the flux is 5.5 Weber and the cross sectional area is 6 into 10 to the power minus 3 meter square. So 6 mm. M means millimeter square. So flux is given by phi, that is equals to 5.5 Weber, and area is also given 6 into 10 to the power minus 3 meter square. You can also write it like this. Now we having flux density formula, that is B equals to phi by A. Substitute the values. Phi equals to 5.5 and area is equals to 0.006. So now B equals to 916.7 Tesla. Tesla is the unit of flux density. And what is the magnetomotive force of a wire with 8 turns carrying 3 amperes of current? So 8 turns, here we having N and 3 amperes. That is means 3 amperes means current. So turns means N. Now we need to find magnetomotive force. So F equals, so magnetomotive force MMF equals to N into I. We having formula. Substitute the values, then you will get 24. The unit of magnetomotive force is ampere turns. And next is the Lenz's law of electromagnetic induction. So it states that the induced electromotive force with different polarities induces a current whose magnetic field opposes the change in magnetic flux through the loop in order to ensure that the original flux is maintained through the loop when the current flows in it. So it means when electromotive force with different polarities induces a current whose magnetic field opposes the change in electric flux through the loop. See, in this diagram we having electron flow, and this is the movement of wire, and this is south and north pole. So why it is used? Because to find the direction of induced electromotive force and current. So so this is proved by Lenz. So it called as Lenz's law. So it depends on the principle of conservation of energy and Newton's third law. Newton's third law we know, right? It states that for every action there is an equal and opposite reaction. So it is most convenient method to determine the direction of induced current. And it states that the direction of induced current is always such as to oppose the change in the circuit or magnetic field that produces it. So induced current having direction, right? That is always opposes the change in the circuit or magnetic field produced it. So this is about the Lenz's law. So we having experiment also. In the Lenz first experiment, he concluded that when the current in the coil flows in the circuit, the magnetic field lines are produced. So when current flows, that time magnetic field lines produced. And when the flow of current in the coil increases, that time magnetic flux will also increases. The direction of flow of induced current that will opposes the increase in magnetic flux. So this is about the Lenz experiment 1. So see in this circuit, here we having, this is about the Lenz experiments. So you can assume like the invisible field. So you send electricity through a wire coil. So then turn on the power. The magnetic field is suddenly born and start growing. Right? The coil does not like this sudden growth. So it creates small back pressure. So that is nothing but induced current. So why it creates means to slow down the field's growth. So when current is more, magnetism also more. So that is nothing but the first experiment. And in the second experiment, he concluded that when the current carrying coil is wound on an iron rod with its left end behaving as N pole and is moved toward the coil S. So an induced current will be produced. When N pole is moved towards the S, induced current will produce. So you push a north pole magnet toward the coil. See here, you push a north pole magnet toward a coil. You move the magnet closer. So the coil feels the magnetic field getting too strong. The coil turns itself into a magnet with north pole facing yours. So why? Because north and north repel. It is trying to push your magnet away to stop the change. The pushing energy is what creates the electricity. So it's like the repelling gust, isn't it? So this is about the second experiment, and next is the third experiment. So in the third experiment, he concluded that when the coil is pulled towards the magnetic flux, the coil linked with it decreases, which means that the area of the coil inside the magnetic field also decreases. According to the Lenz's law, the motion of the coil is opposed when the induced current is applied in the same direction. So to produce the current, force is exerted by the magnet in the loop. To oppose the change, the current on the magnet must exert a force on the magnet. So assume like you pull a coil away from the magnetic field and you pull the coil out of the field. The magnetic strength inside the coil starts to disappear. So now the coil is sad to lose the field. It creates a current to act like a magnet that attracts the field back. You will feel a physical drag like the magnet are trying to hold on to the coil as you pull. So what you got means, in experiment 3, pulling a coil away from a magnet makes electricity that pulls back, isn't it? So in experiment 2, pushing a magnet toward a coil makes electricity that pushes back. But in the first experiment, electricity makes a magnetic field. That's all about Lenz experiment, and next is the dot convention in coupled circuit. So in magnetic circuits and coupled circuits like transformer, here we have the dot convention means it is a marking system. Why it is used means to determine relative polarity of induced voltages without needing to draw out of the physical winding direction of every coil. So here we having core rules. The source of the dot convention lies in the relation between the physical wrap of the wire and Lenz's law. Here we having two primary rules to follow. So first one is the current entering a dot and second one is the current leaving a dot. Here you can see the diagram. So if current enters the dotted terminal of one coil, so if current enters, it induces a voltage in the second coil. So that is positive at its dotted terminal. So current leaving a dot means if current leaves the dotted terminal of one coil, it induces a voltage in the second coil. So that is negative at its dotted terminal. So this is the core rules. So when current enters the dot on the primary side, if current is entering here, the induced voltage on secondary side. So here voltage will induced. That will be positive at the terminal marked with the corresponding dot. So the dot represents start of the windings. If you were to look at the physical core, the wires at both dots would be wrapped in same relative direction. Means both starting from the top and wrapping clockwise. So this is about the dot convention. That's all about the magnetic circuits and electromagnetic induction. For more videos, watch the upcoming videos. Thank you all.